In this video, we want to take a look at the basic properties of addition and scalar multiplication in Rn. So here's the theorem. If u, v, and w are n-tuples, right, or vectors at Rn, however you want to think of them, and k and m are both real numbers, then the following, what do I have? 8 conditions here are true. This is not a equivalent statement thing. This is each of these is true by itself. So we've already seen this, that addition is commutative, addition is associative. There's a zero vector that if you add u plus 0, 0 plus u to anything, it's equal to u. Likewise, the vector negative u added to u is 0. And we've got a couple of distributive properties. That is, if you have a real number multiplied by a sum of two vectors, then it would be the same as multiplying the real number by each vector and then adding them up. Or you could say, what if I'm adding two numbers and then multiplying the result by a vector? Well, that's the same as multiplying the vector times each of the numbers and then adding those two. Here's kind of an associative property for scalar multiplication. So if you got two scalars that you're trying to multiply by this vector u, you can either multiply one of the real numbers in and then the other one in, or you can multiply the two real numbers together first and then multiply it in. And lastly, this one may seem kind of silly, but 1 times u equals u. There's some other properties that we're going to look at down below that I could list here, but the book chooses to list these 8 because of what we're going to do in chapter 4. When we looked at abstract vector spaces, there's certain properties that define the vector space, and then there's other properties that can be proven from those. These are sort of the basic ones, and then the others can build on top of these. Let me prove one of these for you. I'm going to prove, how about number 6 here? Let me prove this one for you. Number 6. The way I would prove this is I would say I've got k plus m, that's an m, may not look like it, times the vector u, which is u1, u2, up to un, commas in between there. And I have a definition. How do I multiply a scalar times a vector? Well, I multiply each component of the vector by that scalar. So I have a big vector here. Well, it's the same size as that one, but it's got more complicated entries in it. So I have k plus m times u1, k plus m times u2, and so on up to k plus m times, that's an m, un. But each entry now here in each component of the vector or of the n-tuple is just real number. So I know by real numbers that this is ku1 plus mu1, comma, this is ku2 plus mu2, and all the way down to kun plus mun. And now it's like, oh, look, that came from, or could have come from, the sum of two vectors, ku1 up to kun plus mu1 up to m times un. But this right here is k times u, and this right here is m times u. There would be a proof that k plus m times u is equal to ku plus mu. Now, each of these proofs is very similar. Show that you can transform the left side into the right side, and really you do it with the components. You know how to add vectors, you know how to multiply by scalars, and you see that you end up with the same thing. And it really boils down to, within each component, you're just dealing with real numbers, and you know the properties of multiplying and adding real numbers. Okay. Now, let's look at my next theorem here. That's and this theorem, I guess it's 3 theorems because I got 3 properties. As I say, I could have written these up here, but really these are provable from those, where these actually have to be looked at individually. And they're pretty obvious, I think, that 0 times any vector is 0. That if you multiply a real number times the 0 vector, it's still the 0 vector. And -1 times any vector is the additive inverse of v. Let me prove this one to you here. Here's a proof of number 1. Take any vector v and add 0 times v to it. By the distributive property, which distributive property? This one that I actually proved here. This is equal to, well, oh wait a minute, a couple of things. By property 8, this is 1v plus 0v, because the v is 1v. And then by property 6 here, I can factor the v out. So this is 1 plus 0 times v, which is just v. Oh, sorry, it's 1 times v, which is v. So what did I do? I took v and I added this to it, and I got v back again. So 0 times v is equal to 0, because that's the additive identity. That's the only one that when you add, there's only one thing that you can add to v and end up with v again, and that's the 0 vector. Okay. Now, I could have just said, look, v is v1, v2, v3 up to vn, and I'm going to multiply by 0, and oh, 0 times v1 is 0. I could have gone to components here, but I didn't want to, because I can show you that this is a consequence of the stuff up here. Okay, this is sort of a higher level property than those. This is based on those. Okay, so anyway, still not surprising, any one of these things. And I want to end this discussion here in this video with a definition. We are going to use this many times, and I think I may have given this definition before. I'm going to reiterate it. A linear combination. Given a finite set of things, S, and these things, I'm writing them as vectors. The book is defining them as vectors, but it doesn't matter if they're things. I got a finite set of things, and a linear combination of this set is a sum of multiples of its elements. That is, I have something that looks like this. Take each one of the things in there, so v1, v2, and v3, multiply them by a real number, and add them up. That's a linear combination. It is a sum of multiples of the things that are in here. Okay. I think early on in the quarter we talked about linear combinations of columns of a vector, or sorry, columns of a matrix. Now the book is talking about linear combinations of vectors. The notion of linear combination is the same no matter what the things are. You're multiplying them by real numbers, and then you're adding up all the results. This is what's called a linear combination. This would be a good definition to know.